Okay, guys, what does, okay, this is about the calendar update. Remind you, we have a test next Wednesday, right? Yeah, test 2. So what happens is that, get 3 tests out of the way. What we do on the first test is we do that on the 5th class. And then after that, we have a test every 4th class. Get 3 tests out of in 8 weeks. And then the last class, of course, will have final exam. Because what they do on the midterm classes, I don't know if you notice, if you look at the final exam schedule, they always schedule it on Friday of that week. So we don't do that. What we do is we give the final exam on the last day of the last class. I guess I don't know. It's probably already on the test is already on the schedule, so we'll have our final exam. So test 3 will be on the 11th, and then the final exam will be on the 13th, which is the last class in here. Not unless y'all want to come in on Friday and do it. But it would be hard for me to do anyway. We're in a committee that meets every Friday, and it's trying to deal with getting more women into career technical programs. I know you'll probably notice there's very few women in technical trade, even though, most of the jobs just about anybody can do. You just got a logical mind and can reason things out. Anybody can do these jobs. So there's actually probably more women in the welding department than there is in mechatronics or mechanics. And it is crazy, huh? So, and that's on every Friday. So that eats up 2 hours of my 7 hours worth of office hours that I have every week. So if I get behind on things this semester, you need to forgive me because I've only got 5 office hours. And guess what last Friday was? I registered people all day. I didn't have any office hours that I could actually grade stuff at. So I'm running a little behind. Like Remind, I just got Remind set up, which is the testing application. Everybody get a text from me? Okay. So should have got 2. I put y'all in the wrong class, by the way. Like I said, I'm sorry about that. So you probably got a text saying, welcome to ECD 226. But later on, you should have got another one. Yeah, I had that class on my mind. I do that a lot. So we're looking at what is an actuator? Well, there's all kinds of stuff that transfers energy. Power into motion, right? So we already have to have our energy converted. So we know we can't create energy. All we can do is just change, right? So we can change one form of energy into another form of energy. So what we're doing, and then of course to get power, we have what we call a power source or power supply that actually provides what we call a difference in potential, which causes things to move. And then of course, what are we moving in here? We're moving fluid, and then we take that fluid and convert it into motion with actuators, right? We have 2 categories, or 3 really. We have linear actuators or cylinders. Then we have rotary actuators, and then we have motors. And everybody understand the difference between a rotary actuator and a motor. So what's the difference? So everybody knows the difference. But when I ask y'all do something. Well, what's the difference between a rotary actuator and a motor? Yeah, it's got what we call a limited stroke. By the way, linear actuators, the stroke is given in inches or millimeters. And then rotary actuators are given in degrees. So it'll have a certain degree of stroke. Okay. And the motor doesn't have a limited stroke. Unless we limit it outside the motor, right? You understand that? More, yeah, multiple rotations of 360 degrees. technically a rotary actuator could go over 360 degrees, but it's going to break sooner or later, right? You understand that? And still be defined as a rotary actuator. So a rotary actuator's got fixed limits to how far it can rotate. So we were looking at the PowerPoint. By the way, any more questions on the test that we need to get out of the way?
Push the bolt.
What's that?
Before you got the flow.
Well, basically we had to deal with, well, we did a little bit with speed. That force is equal to pressure times area. But you got to remember, if you got a cylinder that's it's a single rod cylinder. We do have multiple rod. We have dual rod cylinders. If you got a dual rod cylinder, that means you got a. Let me go ahead and start this one. So I have some place to write. Well, if you got a dual rod cylinder, then what it would be, this would be a symbol of a dual rod cylinder, where we have a piston, and then we have two rods coming out the same size. And of course here, the rods would be the same size, so there's no such thing as push and pull, right? Here we would have to say left, right, up, down, or something like that, because there's no push and pull. But if I've got a single rod cylinder, which is all our questions are written up on. And so what I've got, if I'm pushing on the bottom, I've got the complete diameter that I'm pushing against. If I'm pushing against this side right here, then what I've got is I've got this diameter right there, because that's the only place I'm pushing on. All the rest of them are pushing into the rod. And of course that didn't cause any problems because the pressure is equal all around that rod, right? And the rod can't move. So you can't move it left or can't move it right. But what we have here is we have a piston, and we have a low pressure side and a high pressure side, and now we got high pressure and it's going to move it toward the other, but it's only the area that it's pushing against, right? So the formula is force is equal to area times pressure. Well, if we're extending, then that's true. But if we're retracting, or what is also called a pull, so push would be pushing it out, and pull would be pulling it back, right? Then your force is going to be equal to the area of the piston minus the area of the rod times the pressure. Because that's what we got. That's what we got pushing, right? I don't know, and I think in that question that would be true. Because I think what we had a 4-inch cylinder. You got that backwards. The big area is the area of the piston, which I think was 12.57, right? You understand? And you're going to subtract from that the area of the rod, which was 7.66. And then that would be the amount of area you have when you retract it. Yeah, the push would be the extend, and the retract would be, and I think I went in on the retake, and I actually went in, because that question got asked a little bit. I think I went in on the retake and I put in parentheses retract and extend, and I went back and put that on the actual test too, so y'all wouldn't get those confused. I did? Oh, well. Okay. Go ahead.
I kept seeing blind area.
Huh?
I kept looking and seeing blind area. What's blind area?
On the test?
No, I was going trying to research it.
Oh, I don't know what they mean.
That's for blind area.
That's a new thing on here. You could probably say, define cylinder blind area. I don't know what they're talking about. They might mean what they're talking about, the same thing that we're talking about. The rod area, I don't know. That's a good question. Did you put in the internet define
I did have it. I
Cylinder
can't get
blind.
mine right now.
So any more guys? Yes or no? Well, the speed, what's the speed? Was that question on the test? Okay, so what is the formula for speed?
Like you gotta have a formula to use it. You gotta go through the oil field formula.
Well, it depends on how much they give you on the question. So it depends on what's given. So here, so yeah, I do have it. So here it says what would be the speed for the cylinder. So if we look at our equations, the equation, I don't have the equation. But what's the equation? Like I said, I don't have the book. All I got is the formula sheet. So we got several ways we can calculate that, right? So the answer, you could have gave me several different answers. And what I've done on the key, I think we had 3 different answers we come up with. Because I think your answer, your formula sheet says what? If you got your fluid power book, what does it say? So what does it say? By area. And of course, that's a relative term because that's cubic inches per minute. And the problem is our flow rate is given in gallons per minute, right? So what we have is we have a conversion factor. And what is the speed? No, what is the speed? It's got to be in some unit. It's like miles per hour. When I give speed, I give it in 2 units. I give how far with, I don't know. What is it? For this formula, it's different. So we said different formula in the handout that I gave y'all because that's in feet per second. But the one in the formula book is cubic inches per minute. No, that's the flow rate. That would be like saying how fast you're going, and you say cubic miles per hour. So what speed is given? It's going to be in inches per second. It's going to be in inches per minute. Yeah, so that's what we mean. So your flow rate is a volume. Your speed is in a unit over time, right? You understand that? So this formula they give you in that book is inches per minute, right? And of course, the one I gave you on the formula book is feet per second, but it's no big deal. It's the same thing, right? You don't understand that? Yeah. In fact, usually we normally it'd have to be a pretty fast cylinder, but it would be easy on a short cylinder to use inches per second, right? Okay, so first thing I got to do is I got to come up and what does it say? It says the speed we got. So what's our 2 areas? So my push area I think is 12.57, right? And then my pull area is 7.66, I think, if I remember right. Okay. So that gives us the number we put on the bottom. So now we got to come up, but my flow rate is 8 gallons per minute. So somehow I got to go from 8 gallons per minute to cubic inches per minute. So what's the conversion rate for hydraulic fluid? It's in there somewhere. And that's what's a little nicer about using. That's what's a little nicer about using the formula sheet that you can get, is that it gives you the conversion factor.
Tell them what?
Gallons per minute to cubic inches per minute. Ooh, don't know. That don't sound right to me. Yeah. Somebody found it the other day. Of course, this is nice. This is nice, guys. But what you got to understand, this is a pretty common thing that we use. If it's pretty common, then odds are in this book there's going to be a table out there somewhere, right? Where you can look up your area and compare that to a flow rate, and it gives you the speed. But we'll see how it works out. So what's the conversion factor for gallons per minute to cubic inches per minute? What page is that on? Somebody found it. I think it's number. Huh? I know it is, but this is that book somewhere. Because I swear somebody gave it out in class. Like I said, I don't have a copy of it. So well, we're not there. We're not dealing with that. It's in there. It's 231. So the conversion factor is 231. Page what? Yeah, but it's kind of strange, and it gives you the formula. But what it gives you is it gives you an example. It's in an example, is what it says. Yeah, calculate hydraulic cylinder speed on page 14 under solution. Yeah, I would highlight that. I don't know if there's any highlighters over there. That is a highlighter. It's not a green. I think it's a green mark. Yeah, I think that will cover it up, that you won't be able to see it. So I would say 8. I'd say 8 times 231 divided by the extend would be 12.57. This would be extend. And then I would say speed retract would be 8 times 231 divided by 7.66. Yeah, so it's on page 14, but I don't know if it's anywhere else in that book, but it doesn't tell you, but it gives you a solution for it, right? So what would be my speed extend, and what would be my speed retract? I think 8 times 231 is like 1848 or something. Yeah, that's what I mean. I would use the chart. So we've got 8. Yeah, 1848, then divided by 12.57. That should give you, I think, 147 or something like that. Yeah. And then your extent, your retract speed would be 1848 divided by 7.66, and that would give you your 241. Okay. Now look over there. What table is that on? Okay, look at page 17. And it's got your areas. So what you're doing is you're looking for a 4-inch. Of course, you don't even have to know the area, right? It just gives you the bore. So we're looking for a 4-inch bore. And then move that over to 8 gallons, and it should say 147. And then you find where it says a 1/2-inch rod. So that's down there, 1/2 inch, right? And you follow it over, it should say what? 221? Starts half, 2.5, I'm sorry, 2.5 inch rod. Now 241. So you see, I mean, you can do the math, and then, but you gotta understand that the units is what? Inches per minute. So you just can't throw out numbers, because this guy, if you use the data sheet, if you use the formula sheet that I gave out to the people that didn't have the data book, you're gonna come up with a different answer, because it's in feet per second. So if you throw an answer out there and you don't put the units, and you got all these different things that it could be, right? You understand? Then, so you got to make sure you put the units on there. Yeah. So it's a really, Yeah, but we did. I don't know if y'all remembered. I remember, of course. 231. I have a tendency to keep numbers in my head because it's just a trait I mean. So I wasn't doing the math up here, by the way. I can't multiply 3 times 231 in my head. But I just remembered the answer. But I have a hard time remembering phone numbers at that time. We don't remember phone numbers anymore. Not anymore. I had a guy called and looking for my son. They wanted to know his phone number, and I said, well, I don't have my cell phone. I don't know what it is. He said, you don't know your son's phone number. So guys, we okay? Any more on those? I don't think we're looking at compression factors now. That's coming up here pretty soon. And what we're doing is and I don't know if this book covers it. Does the book in there have anything about CD? No. The data book?
CD to SCFM conversion factor.
Okay, CD. That's a pretty important table. And we're going to talk a little bit about the CD, and we'll look. But everybody all right on the test? We looked at the different types of cylinders, right, that we could get. We didn't talk much about the rings or the seals that they put inside these things. We talked about the different ways of mounting the cylinders. This was pretty interesting too. They give you the illustration. Unfortunately, I hadn't been able to find one for hydraulics. But if you look in under course content, then there's one in there called reference materials. There's a really good data book that I don't know if you want to download it or put it on a thumb drive or not, especially if you get out of here. This is Mead's Pneumatic Application and Reference book. And what we're going to talk about in a minute is something called a CD. It's a coefficient of velocity. But another thing that I like that they provide in the book, of course, they give you all the symbols. These are pneumatic symbols, but a lot of them are crossed between the two systems, right? Very, very similar. We do hydraulics a little different. On pneumatics, what we do to regulate pressure, we use a pressure control valve, right? What we do on hydraulics is we use what we call a pressure relief valve. And we'll look at the difference there. But there's very similarities on what we do there. And the different types of valves, the different types of operators. And then this is CD. We're going to look at that in a minute. And then another thing that I noticed that is pretty interesting is, and if you think about it, this really comes into play. is how much force you need to generate to lift the load. Well, how much force do you have to generate to lift the load? Well, it actually depends on the angle that you're trying to lift it, right? Yeah, this book is on blackboard. And of course, we're not going to deal with this on test, but this is just some place that you get out there and you got to calculate how much force you need, or what size cylinder you need, or what size valve you need to run a system. And most of that stuff is out there available to you, so you don't have to do a lot of math, right? You can look them up in charts. But there is some math involved. So what actually determines the amount of force is required to lift the load is the angle that you're trying to lift it at. So as the angle goes up, your force is you would have to use trig to calculate this out, by the way. But what this would do is this would tell me a multiplier that I would use to determine on how much force I need to generate to lift the load at an angle. Of course, if you're lifting it straight up, then you got to lift the load, right? But if you're pushing it out, then you not only got to move the load, but you also got to overcome the friction that the load is pushing. And then when you start changing that angle, the actual weight is distributed on different angles on what you're pushing, right? Does that make sense? So this is a neat thing. But what I want to do now, guys, is do y'all have a formula for the CD rating of a valve? So what we've got to do is, if I'm going to run a cylinder and I'm trying to run it at a certain speed, then I've got to assure that I get the flow to the inlet of the cylinder. So what sets the speed? It's not the flow in the system. It's the flow that comes into the inlet. It's the inlet of the cylinder, right? So what determines the speed is basically the flow rate. Of course, what determines the force is how much pressure you have. So we could have a lot of pressure in a small flow, or we could have a lot of flow in a little bit of pressure. So the CD rating of a valve is basically how efficient it is of moving fluid through the valve. And this is a U.S. customary, so if you get into valves that are used a lot out of the United States, then you probably won't see a CD rating on a valve. If you get into a company that sells a lot in the United States, even though they're a foreign company, then odds are they're going to list that CD rating on the valve. Because what we can do with that CD rating on the valve is we can do a lot of stuff that's going to limit, make it easy. Valve sizing, both symbols. Well, forces, that's one part of it. Force is equal to what area times pressure. So it's not just a pressure, it's how much area that pressure is pushing it in, right? Yeah, pressure times area. So when we buy compressors, two things that it's going to give us is it's going to give us the maximum pressure that it can generate, and it's also going to give us the flow that it can maintain at different pressures. If you ever look at a compressor, it'll give you basically two values. It'll give you the maximum, so at the maximum pressure, you should have the maximum flow, right? So you're just at the minimum pressure, you're going to have the minimum flow. So if you ever look at a standard compressor that uses an intermittent motor and uses a reservoir, it's going to give you two flow rates. And usually it gives you what we call standard cubic feet per minute. And what is standard cubic feet per minute? Yeah, but it's what is it? What is standard cubic feet per minute? So we say cubic feet per minute. That's good. But the problem that we have with air is that its volume changes with altitude. So that means the higher I move up, the less true volume we're going to pull in per stroke to compress. Right? You understand? So that means the higher in altitude, we're going to lose, the compressor is not going to generate the same pressure. So if I'm going to specify the speed of a compressor, the speed or the volume that the compressor can move, I've got to give it at some reference point. Right? You understand? So what reference point do you think they use? Sea level. So yeah, so standard cubic feet per minute would be the amount of fluid that compressor could move at sea level. And we also have problems with liquid. A lot of people think on a pump, they think that the pump provides the actual pressure. What the pump does is it provides a vacuum or a suction, and what determines the actual pressure is how big your tank is and how much atmospheric pressure is pushing down on that liquid. You understand that? Force is equal to airtime pressure. So this is the problem we have, is that even fluids will have different flow rates at what? Not fluids. Even liquids will have different flow rates at altitude, which is pretty interesting. So CV is a U.S. customary. So just about all your valves sold over here, and it's a really neat feature because just doing a very little math, we can calculate a lot of stuff. So the CV is basically determined. If you look, what does it give? What formula does it give you in your data book for CV rating? Should be a formula in there for CV rating of valve. Now normally you don't have to calculate the CV rating. The CV rating is calculated by the manufacturer. And what they usually use is they usually use water. Because the water has a specific gravity of 1. And they're saying, oh, if I can push one gallon per minute through a valve, 1 gallon in 1 minute, that would mean the valve would have a CV rating of 1. If I did 2 gallons, if the valve could do 2 gallons in 1 minute, 2 gallons of water in 1 minute, then the valve would have a CV rating of 2. So the CV rating, so the higher the CV rating is of a valve, the more flow we can use. Is that in the digital data book? Where's that at? Oh, it's in the textbook. Oh, wow. And it does, the digital data book does not give you the CD?
I don't want to see it.
Yeah, like I said, I don't have a copy of it. I would have looked it up and see if I could have found it in there. You know. And I probably could have helped you a lot finding these formulas. Does it have any charts on there about CD rating? Might have to borrow one of those data books and take it over to my office and scan it. So that way I won't have to worry about keeping up with that copy of that little thing. Last time I taught the class, I had it. But the problem is that we had another instructor that taught the class, and I gave him my material. I did get my book back, which I hadn't. Since I hadn't taught the class for 5 years, it's been gone for 5 years. Like, huh? So this sheet right here, so here it is right here. Value CD flow factor. So this is the formula right here. So what do I need to know? So the valve factor, I need to know the flow rate in gallons per minute. And what do I need to know? The specific gravity, right, divided by the pressure drop. Not the pressure, it's the pressure drop. So by the way, if you look over there on the right hand side, it gives you a break. And normally in engineering, if we use a change in, which would mean I get a different value on this side than I get on that side, or vice versa, what we use is we use the Greek symbol delta. So what that delta means, it means a change in. So it means if I've got 60 psi out and I've got 65 psi in, then that would be, the delta P would be 5. You understand that? And that's what, and we'll run into that a lot, especially in electronics. We ran into it last night in my solid state class, where they had the little delta, and it was a change in one current relative to the change in another current. But you'd have to know the change. You'd have to know how much it changed. So here, this would deal mostly with liquids. So different liquids have different specific gravities. So what I would do is, so if it was water, I could use gallons, I could use flow rate, so, and then I could divide it by the pressure squared, and that would be it, right? But since hydraulics don't use water, then we need to know the specific gravity. The specific gravity of a liquid is relative to water. So what's the specific gravity of water? 1. So you could look up a chart on what fluid you're using, what liquid you're using inside your system, and that would give you the specific gravity of that. I might have to look it up. I don't know. I know a lot of stuff, but I don't know that. But I do know what. I mean, odds are you can go up on the internet, and it would probably come in and do what? Say what's the specific gravity of gasoline. It might vary with the octane rating. I don't know. We could get that pretty easy, right? And that would probably be some of the information that you would. That would probably be some of the information that you could probably also get from the supplier of your fluid, right? That would probably be available in there. And so what we use this guy for is we use it to make sure we get the right size valve to do what we need to do. Okay, does that make sense? In this book, since this is related specifically with pneumatics, it makes it a lot simpler. So this tells us right off the bat, if I know my gallons if I know the CV rating of my valve, and I know the factor according to the pressure that's moving that thing, then I can calculate the amount of cubic feet I can calculate the number of cubic feet per minute that I need. That makes sense? Or if I know my cubic feet and I know the factor of my valves, then I could also calculate, I could flip this around and calculate the CD of the valve that I need. So what would be the formula for the CD rating of the valve? So can you see the formula is using cubic feet per minute equals CP over a factor that they give you out of a table. So standard cubic feet per minute equals to the CV over a conversion factor. So that means if I knew the standard cubic feet per minute that was available for my compressor, how could we solve for CV? So we could come over here and put it in our little formula thing, standard cubic feet per minute, CV over conversion factor. So my CV would be equal to my standard cubic feet per minute times my conversion factor. So what I could do with this is I could do what? I could actually figure out what size ports I need on my valve to handle that speed. And another thing I like about this, and of course, like I said, I couldn't find it on so this is the formula they give. First of all, when we talk about a cylinder, so this what we're trying to do is we're trying to calculate what size valves I need to cause a certain size cylinder to extend its rod at a certain speed. And this is the formula. So first of all, the fluid comes flowing in there. What's the first thing it's got to do? It's got to occupy a certain amount of volume, right? So what? First of all, we need to know the number of cubic inches or whatever is inside that cylinder, the displacement of that cylinder. Then I need what they're calling A, and these are your conversion factors. And this is dealing with the amount of pressure drop that you want through the valve. So I cannot send flow through a valve and not lose any pressure. That would be impossible, right? Understand that. So the ones they give you in your chart is a pressure drop of 2 psi, pressure drop of 5 psi, and a pressure drop of 10 psi. So 2 psi would probably be your bigger valves, and they would be more expensive. 5 would be in the center, and then your 10, a pressure drop of 10, these would be your smaller valves. So that 10 psi drop through your valve would be what? That would be your cheaper valve. Everybody understand that? So normally, which one would you think we would probably use? Huh? Should. It depends on what money you're using to play. Standard, they say, choose a center one, which would be 5 psi. So, I choose 5 psi. I come up here, I say, okay, what's my inlet pressure? I can choose my inlet pressure. Then it's going to give me a conversion factor. Like for 60 psi, my conversion factor would be 5.1. So two things, to calculate the area or the volume needed by the cylinder, I have to take the area times the stroke, right? I understand that. Okay. Then I would multiply it by a pressure drop of A, and then I would multiply it by a conversion factor. So if I have a pressure drop of A of 60, then I would use this right here for A, and then I would use this right here for my conversion. I would use this right here for my conversion factor, and then that would, when I do all that, that would tell me the CV rating of the valve I have. That makes sense? Yes, no? Everybody's going to like this. So let's say if we got one. Let's say I've got we already know the board on this, and we'll just calculate the speed. So let's say I've got 60 psi, and my cylinder's got a 4-inch bore, and we wanted to extend in 5 seconds. Do I have enough information? Let's see. What else do we need? Oh, and we need the stroke. Let's say it has an 8-inch stroke. So in time, I wanted to do in 5 seconds. Okay, so we got enough information. Go write that down. So I got 60 psi. I've got a 4-inch bore. And it's got an 8-inch stroke, and I want it to extend in 5 seconds. Are we okay? Huh? 8-inch stroke. So first thing we would calculate would be the volume. So I would take the area. So we know the area of a 4-inch rod. We've already done that. Is 12.57, right? So I'd take 12.57. I would multiply it times the stroke, which is 8 inches. Yeah, that's just me. I made that up. Are we okay? Everybody doing the math? You doing the math, Jacob? Jacob, you doing the math or you? Huh? Okay, I didn't see that. So what's that? What would be the volume? Everybody okay with that? Huh? Okay. Then I would come down here and I'd look at this chart right here, and we're going to do a 5 psi drop, 60 psi. So at my A value would be 0.054. Yeah, 0.054. Because it's in the chart. All we do is we say, okay, what pressure drop do we want? And we chose 5 psi. Okay. So what pressure drop do we want? 5 psi through the valve. But what I did is I looked up my pressure drop across the valve, and that's what the delta P means. So what that means, I'm putting 60 psi on the inlet, I would be getting 55 psi out. If I use this size valve, right? You understand? Okay. So what I would do is so A is the pressure drop coefficient, I guess you'd call it. So all I do is come over here and I say, okay, my A value would be 0.054. So I take my volume and multiply it by 0.054. Everybody okay? And then I would take that answer and I would multiply that times 5.1, which would be my coefficient. 5.1. Okay. Then what I'm going to do is I'm going to come up here and I'm going to divide that by the amount of time. What did we say? 5 seconds times 29, which is a conversion factor.
27.7 over 5 times 29.
Yeah, that's it. And that would give me the CD value, the minimum CD value that I would use. Now you could use a bigger one, but you better not use a smaller one. So if it doesn't fall onto a standard CD value, what you would do is you would always go to the next standard size. You would go up to the next standard size.
Only 5 times 29. Right, the bottom part on the 6.
Huh?
But the bottom 5 times 29.
Yeah, it's going to be second. Time in seconds. Sorry. Wait till we finish this. So what we got? Don't know. Okay, so we look at a CD rating of like 0.2, right? That makes sense. Yeah. Okay, guys, you'll take 10-minute break.
That chart, we have that. Take a picture.
No, if we have it anytime available, I would. So we couldn't find the chart in the.
But I had a whole lot of thoughts. We lost some. Can I show you, how far I got? See how this is light. It is, math is not regular math. 5
It's
plus
regular
5 is 10.
That's not regular math.
It says,
What's your major?
industrial maintenance.
Oh, industrial maintenance. Y'all do a lot of math in there. Okay?
I don't know math they took us to with algebra. This is,
This is nothing but algebra.
no.
Yeah, it is. Well, it's not even algebra. You don't have to transpose the equation. It's just typing numbers in.
Okay.
So let's write the whole thing down.
I got it up there.
Okay, so here's the formula right here. So my CV rating has got to be equal to the area. So I'm going to come up here and I'm going to say 12.57
Okay, yeah, I got that.
times the stroke. The stroke would be equal to A times A. So I go down here and type the table A, and I look at my pressure. It says 60 PSI with a 8 PSI drop. Okay.
60.
So there's A. Here's 60 PSI. I come over to my pressure drop of 5. So I'm
That's
gonna
what, okay.
So I'm gonna come up here and multiply this by 0.6. I don't know how much that's going. 0.064.
It's 0.054.
60. Okay, I'm sorry. I said I have my glasses down.
But I had got that. Nope.
Then the coefficient of, so next is the coefficient of compression. So this would be times 5.1. Then I'm going to take that. You can enter that together down here. You're going to have to do this inside parentheses because you got two things down here, right?
Okay. Go back to the formula. Okay, so that'd be times 29.
Yeah, so the time, we want 5 seconds
Yeah, I was tracking that.
times 29, which is a constant.
And that's since I put, that's what I keep forgetting to do.
Yeah, well, the problem is if you put 5,
It's going to do the 5 times that first.
well, it's going to divide this by
Divide,
5,
yeah.
and then it's going to multiply your answer times 29.
That's what I'm missing.
Okay. So if you say, if you don't put it inside parentheses, that's what it's going to do.
That's
So
what
it's
I
going
did on.
so as soon as you come up here and add all that, you put 5, then you hit the times key. You don't put, it's going to take this and divide it by 5 and multiply that by 20. Okay, you understand? And that's not right. What it is that it's this. Now, what you can do first is just make a note. You could come over. If you don't want to use parentheses, I'll just clear this out and I'll do the 5 times 29 and I put equal and I'll write that down. I'll put 58 over there.
Okay, you can multiply before you put it up.
Yeah, just do it by itself. Before you do anything, right? You understand? And it maybe put it in the memory of your calculator. So that's one way. So I could say 5 times 29. If I don't want to use parentheses, I do the bottom, everything on the bottom first, and I did enter, and then I'd store that in memory. Okay, we're going to store that in memory A. Yes, I don't know. I have to figure out how to use your memory. Looks like you got many memories.
I don't think I had any yet.
There it is. So 5 times 29 equals. How did we come up with 58 over there? 5 times 29 equals 145. Let's put memory. Store. And we're going to store it in A. Okay, so your answer is stored in A. And then I can say 12.57 times A times 0.054 times 5.1 equals divided by recall shift here. We put it in A. Like that. Recall. A.
I
Huh?
do all the time.
I don't know how the memory
Some of those
works.
you have to do the,
25 store into A, enter. Okay, so 25 is in A. That's clear. And then say here, recall A, 25. Well, why can't it work on that?
145.
Yeah, this is this one down here.
Yeah.
So if you just write it down, you don't even have to use the memory. And now you got them. So 145, I'm going to come up here and I'm going to store it in memory A. Nope, multiplied it. 145, store in memory A. I don't know what you do. Let's see if I have to look that up in the book. But you can still do it this way, right? So what you need to do, if you keep reading parentheses, just go ahead and do everything on the bottom first, and then just do what? Write it down.
So once I get this, all this stuff here, and then I divide that into that, get a CV rating for the valve would be that.
Right. So we'll do that now. So I wrote that down. I'm gonna clear it out. I'm gonna just clear it now. And I'm gonna do the stuff on top. 5.57 times A times 0.054 times 5.1. Then I hit enter. And now I divide that by 145. 145 right. So it'd be 0.2. Yours is in engineer notation. Don't forget to look over there.
Yes.
Valves are not rated in engineer notation. They're just numbers.
So I would move it over.
No, you don't move over anything. Well, yeah, you'd move it over 3 times to the left. 0.2. There's no such thing as a 0.19 valve. But that would be what you get, and then you would look and see what CD ratings are available
At 0.2.
for the valve that you're using, and then you usually go to the next larger. So the bigger the CD number, the better the flow goes. That makes sense?
Yeah.
there's some here, and way past on the clock.
I thought you was going to email it to me.
I ain't have to write file. Oh, yeah, I'll make it. Yeah, I thought you emailed it.
Sure, Carl, you know you missed, I understand that. You missed last lap day. I got my bad. I'll turn it out. But it's your call, you know, if you gotta go, I can understand, I can totally understand that. That's your call. That's your call, but yeah, I appreciate you letting me know that. Hope you disappear, I know what's going on. Oh crap. That's what I didn't do. Yeah.
On down.
Right.
Blowing, the whole road got ready to
They're still pulling on. Yeah, that's what it means, is that if you're using negative, if you're doing a negative force, right, you understand, which means the negative force means I'm not trying to push the weight up, I'm trying to lower it down. Well, the problem is when I'm lowering it down, we have a negative force. So what happens is we got that negative force trying to pull that cylinder trying to pull the rod out of the cylinder. So what that means is the rod has a tendency to drift. Yeah, it'll slide down. If we had meter out, it wouldn't do that because the exhaust is going to hold that back pressure. So this is the hydraulic symbol. So we start off with now look, this is the way we regulate. So on pneumatics, we put our pressure regulator in series with our compressor, right? On hydraulics, we don't use a pressure regulator. We use what we call a pressure relief valve. And y'all see what the pressure relief valve does. So let's look at some symbols. Anybody knows what this is a symbol for? VIOR-RESV. Now, most people call it a tank, but it's technically known as a reservoir, if I can spell it. This is a symbol of a pump. And sometimes what they'll do is they'll put a rod coming in over here, and they'll put the prime mover. So the prime mover, so pumps don't work without a prime mover. And normally we either use a combustion engine or we use an electric motor, right? But we could use water, we could use turbine, like the prime mover for the generators that we have, which is our push for our electric power. You know, those use steam or use water. So we use one or two things as prime mover. This is a pressure relief valve. So what would happen is that if I set this for, for 500 psi, then that means anything over 500 psi would be vented back to tank. And that would maintain 500 psi on the hydraulic system. So our pressure regulator, we use pressure regulators in pneumatics. In hydraulics, we use pressure relief valves.
What was the pressure in the line?
Well, anytime, what the pump does, it provides flow. As soon as that flow pushes against something, it provides pressure. The problem is, if it don't move, then your pump's gonna try to create as much pressure as you possibly can get. And what could you do then? You could blow seals and all kinds of stuff, right? You understand that? So this would be if your actuator sticks or something like that. I think you ran into that on one of your garbage trucks where y'all were working on the slides on the compressor and it kept locking up on you. Well, if you didn't have a pressure relief valve, and then that pump's going to it's going to build up as much pressure as it possibly can, and you're going to start doing what? You're going to blow seals. So normally what we do is we regulate the pressure of a hydraulic system just like we regulate the pressure of a pneumatic system, but what we regulate it a different way. So what we do on a regulator for a pneumatic system is we automatically control the size of the orifice to maintain a pressure drop across the valve, right? You understand that? What we do on pneumatics is we have what we call, fluid power, or hydraulics, we use what we call a pressure relief valve. So what it does, it opens at a certain pressure. It regulates at a certain pressure, but what does it do? What does it do with the rest of the pressure? Well, it vents it back to tank. It just takes it back to tank. So odds are, if you're looking at a fluid power system, you're constantly got fluid coming back in the tank. Now, what causes that fluid to come back in the tank when it's being used is that what? Is that pressure relief valve. And so now you can set the pressure of the hydraulic system. And if you know what the pressure is, then you can do some calculations, right? And then you can make sure you use the right seals that would not bust.
Hydraulic
pressure regulator, right? So if this is pneumatics, the pressure regulator would be here. And so what we do is we regulate the flow through it, right? What we do here is that with a pressure relief valve, is anything above the pressure is just going to be vented back to tank. So all that flow trying to create all that pressure just goes back to tank. And now if we operate at a certain pressure, we're going to understand the flow, and now we can figure out what things are going to do, right? You understand that? So this is the tank. So this is the symbol for a tank with a bottom return. So the return actually comes into the bottom of the tank. We don't want the return to be dropping the fluid through the air, because what happens when fluid hits the surface of another fluid? Creates what? Well, not turbine, creates bubbles. That's not good in a hydraulic system. So normally what we do is the hydraulic tank, and we'll show the actual reservoir will literally have a baffle in it. And what happens is your return would come in on one side, and then your feed would be off over here. So what happens is your suction pipe never comes up to the top. It actually pulls off the bottom.
If you have air in the hydraulic line, you know how we have
Compressive.
you know how over in the bottom side we have the devices that build up pressure for when you lose power. It keeps pressure where the machine, the robot doesn't drop. Same type of thing with this. Like, let's say you got air in the hydraulic line. Is there something that would keep, like, on a Bobcat, you've got a bit that goes like,
Not that I know of.
air in the hydraulic line. Is there anything that would help? Now it would fall.
Yeah. Well, it would fall depending on how much air you have. Yeah, because the problem we have with air is it's compressible, right? You understand? So anything that would push against it would cause the hydraulic fluid, instead of maintaining a constant pressure. We even run into that with brake, even now on brakes on your car. So anytime they replace a cylinder or something on your car, they bleed it, and that's what they're
Like
doing.
an old water machine, like one of those lines, the air would rise to the hydraulic fluid line, like it wouldn't mix.
Yeah, it does, but you can bleed a hydraulic system just like you do. You can bleed any hydraulic system. What you do is you just go somewhere at your actuator, and then you just open it up and just let the fluid run out until it's a constant stream.
Right.
I don't know if anybody's ever bled brakes. If you bled brakes on cars, it's basically the same thing.
I never done on hydraulic.
We would do the same thing in a hydraulic system. So anytime you get air in the system, you would do what? It'd bleed it. And you can tell because your cylinders are going to drift on you. Your cylinders are drift for two different reasons. If you got bad seals, bad seals will cause them to drift. And also if you got air in your air line. So this directional control valve, what would we say about that directional control valve? Looks like it's a four-way. Four-way. So it'd be a three-way valve, manually operated, right, spring centered. Because it's a three-way valve. Three-position valve. And it's got what we call a closed center. So what this guy here is what we're going to do here is that it's going to maintain pressure at whatever that relief valve has on it. You understand? Because what it's doing when it's in this center position, this is pushing against an end stop. So if we got this thing set for 500 psi, then we'd always have 500 psi in our system, right? You understand? A lot of times, so this would be what they call a closed center. But what it's going to do, it's going to lock our actuator. And why is it going to lock our actuator? Why is it going to lock? How does it lock our actuator? Well, the fluid has nowhere to go. So if I come over and push on this side, it's going to try to vent the fuel out here, and it comes up and hits a dead stop, right? You understand? If I try to pull the cylinder out, it's going to try to vent fluid through here, and it goes between a dead stop. So what this would do is you could not move that cylinder up there. If it was air, you could move it a little bit because of the compressibility of air. But if it's hydraulic, if you close that center like that, you cannot move that actuator. You cannot move it. But what's nice about this is we can stop it anywhere within our stroke. And you see that's a lot of times, we want to stop that thing within we don't want it to go to the full stroke of the actuator. We want to stop it somewhere in the center. You see these guys with these earth moving equipment, what can they do? They can stop that actuator any way they want to. They have a little handle, and then they let go of it, and the dang thing stays exactly where it's at because it's locked. It's got a closed center. And the fluid can't go anywhere. If the fluid can't go anywhere, unless it's got a leaky seal, then it's locked in position. And then of course here, instead of venting it to air, if we do come through the valve, we got to return it back to what? We got to return it back to the reservoir. What are we using here? Meter in or meter out? Huh? So when it comes in this way, when I extend it, let me erase all this. So when I extend it, here we come up here, right? And of course, to extend it, we would have to have our valve shifted this way. So that would come up here, go through here because it's shifted. It'll come up here. Now, what's it going to go here? Is it going to go through the check valve or is it going to go through the flow control valve? Yeah, because the check valve is going to seat that thing, right? So it's going to go through the flow control valve and we hit this side and the thing extends. So here we're using meter in. Okay, so we come up here and of course it would come out through here. Since we got it shifted up here, it's going to go through this direction and it's going to go back to what? It's going to go back to the reservoir. If I come up here and retract it, so now we're shifting it back the other way. Here it comes out of my tank, comes up through the pump. Now we're going to go through this guy. It's going to come through here, go here, which means it's going to send it out this one. It's going to come over here and it's going to hit that. Okay, which is going to cause it to retract. It's going to come out here. Which way is it going? It's going that way, right? And then it's going to come back, and then it's going to come out the bottom and go back to tank. So we're meter in on extend. We don't do any metering on retracting. So what would happen is we're controlling the extend speed, but retract is going to be extremely fast. It's going to be the flow. It's going to be determined by the flow rate of the fluid, not the flow rate of through the flow control valve, right? You understand that? So this would be meter in on extend. If I wanted to meter in if I wanted to meter in all the time on both extend and retract, then what we would do is we would come down here and put the flow control. We put another flow control valve right here. And if the arrow points toward the cylinder, it's meter in. If it points away from the cylinder, on the check valve. So what we do is just look at the check valve. If it points toward the cylinder, if the arrowhead on the check valve points toward the cylinders, it's meter in. If it points away from the cylinders, it's what? Meter out. So it's real fast. Huh? Because here we would be metering on, we'd be throttling on extend and retract. But still we're using meter in on this, right? If you're using a single acting cylinder though, guys, you only got one option on a single acting cylinder. And meter in. Meter in is the only option you got on a single acting cylinder. Control its speed. That's the only thing you got. Because you don't, so on a meter out, we meter the exhaust. Well, on a single acting cylinder, the exhaust is just a little hole out there, right? You understand? So, that's a good question too. So when in doubt, meter out, but on a single acting cylinder, guys, you only got one option, and that's the meter in. Everybody understand that? Meter out. Can provide accurate control for positive and negative loads. Prime mover is always operating against the maximum pressure setting of the system relief valve. So this is meter out. But notice, how do I know that? Just by looking at it. I look at my unidirectional flow control valve or one-way. They don't call it. They call it a one-way flow control valve. And I see that on my check valve, the arrow is pointing what? Pointing out. Pointing out, meter out. Pointing in, meter in. That's the best way to do it. Here we're not metering the. Here we're not metering the. I'm sorry, we are metering the extend, right? Are you okay? Any questions?
The hydraulic symbol is
The hydraulic symbol First of all, hydraulic. We know we're in hydraulics right off the bat if we see one of these. That's the reservoir. Also, we know we're in hydraulics because the arrowhead is colored in.
Alright.
So on your actuators, they do it sometimes on actuators too, guys. Over here, if you ever see this, and you come over here on these inlets and you see that little thing right there and it's colored in, then you know that is a hydraulic cylinder. Now here, it's not standard, but you'll see it all the time. But we can definitely tell on our motors, and we can definitely tell on our pumps. So if I come over here and draw this same symbol, and I put that arrowhead and I don't fill it in, then that's a pneumatic. That make sense? Yeah, that's the single position valve. That's a 3-way valve. And then, but you still got to specify how it's operated. Valve D is a flow control valve. But like I said, guys, and this shows it as individual units. But we use this technique so often that what do they do now? Put it together. That would be, so valve C would be the check valve. Valve D would be the flow control valve. Yes, because well, on a double acting, but yeah, it drops over to the return side, which returns it to tank. Of course, it's used. It depends. Like I said, to do throttle in both directions, you have to have a flow control on both of them, right? But it's still either going to be meter in, it's going to be meter out, depending on the direction of the check valve. So if the check valves are pointing in, it's what? It's meter in. If they're pointing out, it's meter out. And that's the easiest way to remember. But look at the similarities between a pneumatic system and a hydraulic system. There's very few differences right now. The only difference we see is how it regulates the pressure. So a hydraulic system uses a pressure release valve, and a pneumatic system uses a pressure regulator, right? The pressure regulator is in series with the source, with the power source on a pneumatic system. It's in parallel with the pump on a hydraulic system. I'll take a break. Right. Except for single acting cylinder. Alfonso didn't come back in. I don't know where he's at. That's okay. It's his responsibility to get back in class on time. This is another chart where you can select a cylinder using what we call a power factor. And I couldn't find this in your book either. I need to check and see where this came from. Is this in the textbook? But you got charts that you can do this. So we got a chart that gives us the cylinder force, right, which is on page 15. But it would be a little harder to use because you have to find, first of all, you have to have your PSI out there. You have to know your PSI. And then you got to know what? Yeah, you need to know the diameter. But you'd have to find it inside. You'd have to find your force inside of it. So if I wanted to generate 900 PSI force, what would I use? Well, I would use one side if it was 1,000 PSI. It's not even available on 2,500 PSI that I can see. At 500 PSI, I would probably use a 900. If you don't have 900, what would you do? Go to the next higher. It's not the next lower. You'd have to go to the next higher. Well, using this little formula right here, or using this little table right here, what we can do is we can literally calculate the area or the size of the cylinder we need, depending on the PSI we're using. So here they says we want to, at 80 PSI, we want to lift 900 pounds. So what I would do is I just take the 900 pounds, I divide it by the PSI, and then it comes up and gives me this number, 11.25. Then what I can do is find 11.25 in my chart. And if it's not in there, I just go up to the next one, and it tells me right off the bat I would use a cylinder with a 4-inch bore. Y'all see that? That's pretty neat, right? So you can either look, take all day looking in that chart, right? You understand? But if you had this little chart, you could figure out the bore in no time. I came up here and just say, okay, so what do we want to do? Just give me something. How many pounds y'all want to lift up? Huh? Yeah, just make up one. How many pounds y'all want to lift? How much pounds are forward? Okay, so I want 1,500 pounds. At what PSI? Huh? Okay, 1250. So I'd come up and I'd say, okay, I'd say 1,500 divided by 1250.
That's 1 point.
You got 1.5? Okay, if you got 1.2, then you use a cylinder that's got a 1.5 inch bore. But if it comes up to be in between, you go up, right? You understand? No. So what I'm saying, instead of me trying to go through that whole dang chart, trying to find the cylinder that gives me a bore, with this little equation, all you say, I want to lift this much weight at this much pressure. You find that out, it gives you a number, you go up there and find that number, you see what size bore it gives you. 1250 PSI, yeah.
I wanted to do it that way, put the rod count, like how far I want to
Huh?
I did rod down minimum rod down.
Yeah, well, that's what something, all we're talking about, how much area. Well, I don't think they should, maybe they shouldn't use the term bore, because this is how much area you're pushing. Well, the rod would change your area. So, you understand? So what you do is you look up, make sure you look under the line. What do you say, Charles?
That's not that chart that you read out.
No, there's no book there. This is not in there. I'll look through Mr. Alfonso's. Alfonso's, and I couldn't find it.
That's, I was trying to.
But if Courtney brings his book tomorrow night to class, I'm going to scan it.
So, if you're going to talk about something, why would you want to?
What we do is what we're doing is we're calculating this factor right here. And what I do is I just find that, so this come up and gave me 1.2. Well, there's no 1.2 up there. Go to the next side. And then all I have to do now is just look at the bore size or the area. It's the area, it's actually the area size. So normally when they're talking about the lift, they're talking about the push, not pull, right? Oh, what's this? What did I get this? Oh. Let's bring tomorrow night. Bring tomorrow night. You got the same book, right? I'm not guaranteed. I won't.
So before that, that's the piston diameter.
Well, it's the area. But it depends on what you're trying to do with your cylinder. This is kind of misleading because that would be the bolt. That would be push bore, right? Yeah, but remember if you're lifting if you're doing a negative lift, then you're going to be lifting from the rod side. So what you'd have to do, you know what I mean by negative lift, right? These things still need to be above. So think this would be a little better if they said the area instead of the bore, because when we talk about the bore, we're talking about, on a single, on a single rod cylinder, we're talking about push or 16. We wouldn't be able to do this if we were on the frac side. So this little thing would be more correct if they said the area. Right? Make sense? And I asked me where I got that. I don't have sauce here. These are bores relative to force. I think this is what they got in your textbook, right? So I have a bore relative to force. The data book, I'm sorry. Yeah, y'all got a really extensive one there. Does it cover the one that I looked at? The one that I looked at looks like it's nothing but hydraulic. Because what's your lowest pressure on that? I think it was on page 12. Page 12. Then where's that?
That's on page 15.
That's hydraulic. Do they have another one for pneumatic? This looks like the chart for pneumatics, and it does say that it says table 4-1. Yeah. But the problem we would have here is that we'd have to, of course, what I could do, I guess, is if I knew I had 60 PSI, I could just look all the way down the 60 PSI column, right? Are we okay? Yeah, because that's just PSI. PSI is not relative to, it's relative to fluid power. So if I put so much pressure, I don't care if it's liquid pressure. So force is equal to area times pressure. Is that fluid, is that liquid pressure or is it pneumatic pressure? It's just pressure. So yeah, that would work for either hydraulic or fluid. It's just that when they lay out your chart, you notice your fluid, your liquid chart starts at, I don't know what it starts at, 500 PSI. Yeah. And then your pneumatic chart starts at 40 and goes through 110, which is about the range of what we call a single stage compressor. If you have a dual or a 3-stage compressor, then this chart won't do you good. So a dual stage compressor, we can get up probably around 100, 200 PSI out of a dual stage. A 3-stage compressor, you can get, I don't know how much. For every stage you run that compression through, you can get more pressure, right? So I saw like a 7-stage compressor that they were running, and that's when they got, I think, about 2,000 PSI. Pretty good. Very expensive, but pretty good. So most of the compressors we see is what we call a single stage compressor. I think the one they got in here, the one we got over in the hall building is what we call a 2-stage compressor. So what you do is you take the output of one compressor and you feed it to the input of another compressor. So you increase it. And your second stage is going to be a smaller cylinder. So you can tell these things. So your first stage is going to be real big. Your second stage is going to be fairly small, because what you're doing is you're taking fluid that's already compressed and compressing it more. So you don't want to take it out of this and put it in the same size cylinder, because if you did that, it would uncompress, right? So we'll look at that. That's in here. So this is what I'm talking about. So this is a valve, and you notice over there right over there, the third column from the right is the CD rating on this valve, which has got a CD rating of 1.68. And odds are you're going to see, but that's if you have 100 standard cubic feet per minute at 100 PSI. Are we okay? That's in the chart again. We worked some problems. We've already done that. That's the same chart that was on there before. Symbols, guys. We need to understand symbols. If we can't understand symbols, we can't understand. Okay. So is everybody okay on these? This is a symbol that we haven't talked about. Well, normally, if you've got a piston and you've got a rod, well, what can the piston do? The piston can literally rotate, right? Okay. Well, if we don't want it to rotate, then we have to. So that's a non-rotating cylinder. That means that sucker won't do what? Somehow inside there they won't let it rotate. Now how they do that, I don't know. Everybody okay on cushions? Yeah, so it says non-rotating, right? Everybody okay on cushions? What's cushions do for us? Well, it actually slows, what a cushion does is it actually slows it down before it gets to the end, right? They can be fixed or they can be variable. How do we know which ones are variable? Got the arrow to it, right? Everybody okay? I don't know what this is a cylinder with built-in check valves. Built-in flow control. This one is meter out. It looks like both of them's meter out. They're so small. I don't know what this one is. Stroke reading cylinder. I don't have the slightest idea. I've never seen one. Stroke reading cylinder. So I can't help you on that, guys. But this would be, so if you went over, I don't know, so you can buy the cylinders with the flow control built into them. Now, of course, the cylinders would be cheaper probably to buy instead of buying what? The cylinders plus the flow control valves, but they would be more expensive to replace. That makes sense? Because if I had flow control valves, if I had them separate, I could change the flow control valve. Here, if I got a problem with the flow control valve, I have to change the rod. With cushions, everybody okay there? Cushions would be I think way back on the very first. Okay. So what we have here, you notice when the rod retracts, it goes into a little slot. As soon as it goes into that little slot, then the fluid would stop, and it would stop right there unless it vents out. So you notice what we have here. So here's the cushion right here. Let me put it in a color that y'all can see. So here's the cushion right here. So when this rod comes in here and seats in that, now the fluid appears to be blocked. But if you noticed, it's got what? It's got little veins that come around here. So what happens is that when it hits this, it's going to flow, but it's going to be restricted because of the size of the piping coming back. You can't see it right here, but what we have right here is there's check valves in here too, but you can't see it. But so it's got check valves, and then also what we have is down here we might have a screw, and then I can come in here and I can vary the size of the orifice. Well, if I can vary the size of the orifice, then I can control the flow coming from the cushion. Does that make sense? So what happens on these is they'll be flying, and right when they hit the end, they're going to slow down real fast. So they're not going to ever hit against the side, right? You understand? So this would be a variable cushion, but it's only on one side. So what I would do on this one is this guy here would have this symbol right here. So I come over here, I put my piston, I put my rod, and then I would put the cushion on this side. If it's got that, what does it mean? It's cushion on both retract and extend. If I come over here and do this, what does that mean? It means it's variable. Anytime, and this is true even in electronics, guys. If I've got a symbol and it's got a slanted arrow on it, it means it is adjustable. Well, we can adjust how much it slows down. So we can make it hit that thing and slow down a lot and then creep in, right, to understand. Or we can make it come in and hit it and slow and go a little faster. So it's up to you on a variable cushion. If you have a fixed cushion, then you don't have the ability to change the rate it accelerates when it hits that cushion. So this is like your car. When you're going to bring your car to a stop, what do? You slow down before you come to a stop. Anytime you come up here and you beat something up against the side, you're going to have problems sooner or later. So they do have, those are not usually indicated. A lot of times they'll have like a rubberized thing up against the caps. So it don't actually hit the caps, it actually hits that thing. I forgot what they call that. No, it's called something else. So this is really good on your cushions right here. So on this one right here, if I can adjust this guy right here, then I can adjust how much it flows back through that back channel, and I can control the speed of the acceleration. So that answers your question. Okay. This is a symbol for a rotary actuator. This is a bidirectional rotary actuator. This is pneumatic. If it was hydraulic, what would it be? The triangle would be colored in, right? I understand. So since I've got it on both sides, it means this is bidirectional, which means we can cause it to rotate one direction, and then it's double acting, which means we use fluid to do what? Rotate it out. So how are we going to do that rotary motion? So these are the popular methods. We use what we call a helical spline. So what happens is like this guy right here is fixed and it rides in these teeth and my pressure comes up and pushes. What will the thing do? It will rotate to follow those grooves, right? Then we have this has been used for years on railroad trains. The old steam engines, y'all see, the enclosed piston crank. You ever seen the old steam engine where they got the pistons on the side, but the wheels do what? They roll. Well, this is exactly what they use up there. They just use a crank that's offset, and when they push it, it causes it to do what? Move past. Then we have what they call a yoke. So what we have on the yoke side is we have two pistons, and then when they push, it's just got a slot in them, and it just moves it over, right? Understand? Then we have what we call a rack and pinion. So a rack and pinion, what would it do? It's got two cylinders, but y'all know what a rack and pinion is?
Cat ears.
Yeah, this is what we used to use for years when we drove our cars. It had a rack and pinion. So you turn your steering wheel, and it had what we call a pinion gear. And when the pinion gear turned, it had another straight rod. So you have the rack. So the rack is the straight one. It's got gear knotted in it. And when you turn the pinion, which is the round gear, it would make the rod move back and forth. And that's the way we drove cars for years. Now we do it hydraulically through power steering. But the rack and pinion is usually still there. It's just that we move one of them with hydraulics now instead of moving. Because if you didn't, if you lost your power on your car, you wouldn't be able to steer it.
I'll show you the bypass.
Well, that's what you do. You know, most cars you can still stop, even though our brakes are hydraulic, we can still stop even if our car is not running, right?
It's pressurized.
Yeah. So we still have a manual way that we can override the diaphragm out there that actually provides the pressure. And then piston and chain. So these are different ways. All we're trying to do is take a linear motion, and convert it into a what? A rotary motion. The two we have over on our manufacturing line, And there's one that's missing. Good gracious. And this one that's used all the time. We call it a vane type. So a vane type just has a rotary vane in here. And then it's usually got some stops on it. And then when we come over here and put pressure on one side, what does it do? Causes it to swing one way. We put it on the other side, it causes it to swing the other. This is called a vane, and I don't know how that didn't get in the PowerPoint. Are you okay? Any questions? So vane type, helical gear, rack and pinion. The ones we have over on the Festo line, we have a vane type. It's pretty obvious. On the Amtro line, we have a rack and pinion. And the new trainer we just got in, it's called a Boss trainer. It uses a rack and pinion. It's pretty simple. Rack and pinion, you're going to have two pistons on each side. Fluid power motors. I know y'all hate these long classes, guys. Converts full power to a rotary motion energy, and it has an unlimited stroke. Y'all understand that? But here we don't deal with area. We deal with what we call displacement. What is displacement? What is displacement? The motors deal with displacement. So if I've got no. It could be. If I got a reciprocating compressor that's got one piston in it, then its volume would be the displacement. So what's the displacement, guys? When I give an engine and I say it's. So we've already talked about this. Kevin, you okay? So what is displacement? You already know. What's displacement? It's how much volume of fluid you can move in one revolution. So when we deal with motors or actuators, we're dealing with an arc, right? So the stroke is not given. So what we're dealing with, we're dealing with displacement. And we start dealing with these motors. Are we okay? Yeah, well, yes, so motors, pumps, not motors, pumps, and also motors, when we start generating force, then we're going to deal with displacement, right? But when we deal with AC motors, we're going to be dealing with horsepower and that kind of stuff. So it's another unit altogether. Here we're talking about fluid. So here's our symbols. Does that make sense? So these are the true symbols. So normally it has a little. So this would be where we would connect the prime mover. So all your motors, that would be the output shaft. This is the motor. So do y'all understand the symbols? Yes or no?
No.
Well, let's look at it. It'd be nice if we understood. So if the arrow's pointing in, it's a motor. If the arrow's pointing out, it's either going to be a pump or a compressor. Here, y'all see the arrows here. So that means fluid is flowing in and not flowing out. So if the arrow points in, it's a motor. If it points out, it's what? Well, it's a power source. It's either a pump or a compressor. If it's filled in, it's hydraulic. If the arrow's not filled in, it's pneumatic. If it's got two arrows, one on the top and one on the bottom, pointing in, it's a bidirectional motor. If it's pointing out, it's a power source. If it's pointing in, it's a motor or an actuator. That makes sense. So what they're doing is they're pointing the direction of the fluid. If it's pointing in, then it's got to be using that fluid for something. If it's pointing out, it's going to be coming out of the unit, right? Then we put an arrow through it. What does the arrow mean? variable displacement. Right? You understand that? So variable displacement. So we have the ability on some of these motors to change the displacement, which is pretty neat. Are we okay? Unidirectional, are you okay? Should be. Symbols are very important. So I imagine these will be on the test. So y'all see unidirectional. What do we do on unidirectional? Unidirectional means it's only what? One way. Now which way is it? I don't know. That would probably be specified on when you buy the motor. It's either going to run clockwise or counterclockwise depending on how it's designed, right? You understand that? I had a motor that went out on the blower motor on my air conditioner went out that actually ran through the evaporator.
But if you have a motor, it can, if you go in, and it go back the other way, you work.
You could if it's available for you to do it. The problem is on motors you have to change, especially single phase motors, you have to change the relationship between the start winding and the run winding. If you don't know where the start winding's at, and you don't know where the run winding's out, and all the wiring is done within the route, so there's a lot of motors that are unreversible. You would literally have to rewind the motor to make it run in the opposite direction. There are some motors that are reversible, and they'll put a little plate on it and pull it off. But still, you got to understand what's the start winding, what's the run winding, all that kind of stuff. So there is a lot of motors that are made non-reversible.
I know fans, it's a switch, but the blade, which makes it clockwise.
No, you're talking about a ceiling fan. A lot of motors that we put on units that always run in the same direction. So a pump, if I got a swimming pool pump, the sucker's gonna run in the same direction. There's no need to reverse it because you don't want to reverse the flow. Right? Some of the pumps do. If you got a big underground, a lot of your pumps give you the ability to reverse them so you can backfeed it or clean out your filter. So air conditioners all blow in the same direction. So if I've got a fan that's on a stand, you can't reverse that. So it's an unreversible motor. So what happened to me was when my evaporator motor went out, somebody gave me a motor, but it ran in the wrong direction. So instead of mine pulling air in and blowing air up to the top, mine blew air out. It still worked, but it wasn't as efficient. I read that thing on that thing for about 5 years, and it finally gave up. But anyway, but the motor was free. But that motor was unreversible. You couldn't reverse it. So these guys, these unidirectional motors, these are done mechanically. So these odds are to reverse them, you would literally have to take them apart and just turn everything inside what? Around. And if you got a shaft that's pointed somewhere, by the way, guys, Kelvin, if you go to sleep, go out there and find your chair and go to sleep. I don't like people sleeping in my class. I'll count you here. Just let me know. Also, you too over there. It really bothers me when somebody answers a question. They're sitting like that when I'm trying to answer it. Go ahead.
Oh, I thought we were still on break line. I didn't realize I don't know. Well, he's got it knocked out for a second.
So on the right, what are these? Pneumatic. On the right, these are what? Hydraulics. What's the difference in the symbols? Yeah, it's just the arrow is colored in and colored out, right? These are just specifications on the motors that they sell, so you can see what they're going to give, how much flow they require. So the motors we got, y'all see the problems with the motors, the pneumatic motors we got. What's the problem? Yeah, so the fluid power motors did not come with the trainer. So Nancy bought those separate. But there's some things that she didn't really consider when she bought them.
Oh, that's you.
So what, some of y'all have had the problem. You get the motor, they don't even rotate. So the motor is actually too big for our valve. Did y'all notice that? Some of y'all had the same. Yeah, well, once it started, once you override the friction, they ran fine, right? But they all run real slow. Y'all notice how slow the motors run? And what's the problem? Well, the motor is actually what? Too big for our system. I mean, it's fine. I don't forgot what deal she got. And so she didn't get them through Festo, I don't think. I don't think Festo motors like that. So this would be a chart. One thing they say, how much it's going to require cubic inch per revolution. So that would be the displacement, right? Revolutions per minute. If we give it the right flow, it would be 936. Continuous intermediate, continuous run or intermediate run. Y'all understand the difference between those? Max bar or PSI. So the bars are on top. So that would be in the international standard. Of course, we're still using what over here? PSI. The next is our torque. What is torque? Yeah, it's a turning force. How much force it can generate when it turns, right? Then it also gives us the horsepower of the motor. And then what's that on the other side? Minimum starting torque. And it's basic, it gives it in several different languages. So that would be the minimum starting torque. The maximum differential pressure would be the maximum pressure in and the maximum pressure out. So you have to be careful if you use an external flow control on this one, because what you'll do when you're controlling the speed is you're changing the differential pressure across the motor. So if I'm putting 50 psi on this side and I got a back pressure on this side of 5 psi, then my psi would be 45. And that would be even if we didn't have a flow control. So unfortunately, anytime we push air through anything or push fluid through anything, we're going to get a pressure drop. Here they call it a back pressure because it's on the exhaust or the tank side. Are we okay? Did I talk around that question? Okay, guys, I'll go ahead and take another 2-minute break for y'all to go to slow home. Everybody get up, walk around, get up. Go put some water in your face, go get your drink of water.
As soon as this is out, my system will go back to sleep.
Oh, you got an energy drink or something?
That's the only way I can stay awake, and that's bad. Like, I was not doing the energy drinks for a while, but then when I started working for this guy, like in the afternoons, I started getting like.
I think you could probably get hooked on those things, too.
Yes, and that's the thing that I'm worried about, because I do crash every now and then, and these aren't good for your heart. These are horrible.
I know, they make the heart rate go up.
Yeah.
I mean, well, look at what's in them. I mean,
We don't do that right now. If I add 4 grams of sugar in it right then.
Yeah, I mean,
That's like,
it's horrible.
This class gets out at 1. Yeah, that's probably, just to get out of the boredom of class, I think we could probably finish this up next class. I think what we'll probably do when everybody gets back